These notes are for energy, and they start at phase changes, and this is for worksheet 1, the back of it, which are the phase change problems. So what is a phase change? A phase change is defined as a temperature at which a substance changes phase. Either going a solid to a liquid or a liquid to a solid, a liquid to a gas or a gas to a liquid. Make sure you know these words: melting, freezing, evaporation, or condensation. The temperature remains the same during the phase change. So an ice cube will melt, and in that process, in a container, it'll all stay at the same temperature until all of it's melted. Once all of it's melted and heat is still being absorbed, the temperature will rise. So water boils at 100 degrees Celsius and 1 atmosphere pressure. Once liquid water reaches 100 degrees Celsius, the water does not get any hotter no matter how much energy is supplied. If the temperature of the boiling water is not changing, where is all that heat going? And when will the temperature change? Well, the temperature will change. For example, this is not liquid water, this is some other substance, and this is a heating curve, and typical heating curves have 3 positive sloped parts and 2 flat lines, so to speak. In the first part here, the substance is a solid from that temperature up to there, and at that temperature it starts to melt, and it takes a lot of energy to be put into it to keep it melting, and then once it's all melted, the temperature can rise, and it reaches another flat line where it has to absorb a lot of energy until every last molecule of the liquid is turned into a gas. So the temperature stays the same until all the energy is overcome by the input of heat or energy to make every last bit of the molecules separate and turn into a gas. Here's another phase change diagram. This one is for water. You can see that water melts at 0 degrees Celsius and it boils at 100 degrees Celsius. And we got the solid, the liquid, and the vapor, or you can say gas. Excuse me. So during a phase change, more energy is being applied, but the temperature does not change, since the average kinetic energy of the molecules does not change. Where is the energy going? The energy is being used to overcome the intermolecular forces. Those are attractions between molecules. The energy is weakening these attractions, so the solid turns into a liquid or a liquid turns into a gas. The big idea is a transfer of heat does not always result in a temperature change. For example, if you're at a phase change, you do not get a temperature change. So heat of fusion is the heat energy required to change a substance from a solid to a liquid or a liquid to a solid. So that's at the flat line. And the heat of vaporization is at the upper flat line, the heat energy required to change a substance from a liquid to a gas, or the reverse. So here's a table of fusion and vaporization. These numbers tend to be given to you on a test. And here's some more values. I know you're excited about these. So using heat of fusion and vaporization. So if 6 grams of liquid gold is poured into a mold to make a gold ring, how much energy in calories is transferred from the ring when it solidifies? So we know the mass is 6 grams, and we know the heat of fusion is 15.4 calories per gram. You could just use unit cancellation to arrive at your answer, or perhaps you can remember that at the phase change, Q is heat of fusion times mass. And you have the heat of fusion, 15.4 calories per gram, times the mass, 6 grams, which equals 92.4 calories of heat lost. Phase change and heat of fusion problem. What is the final temperature if 11 grams of ice at 0 degrees Celsius is added to 100 grams of 20 degrees Celsius water? This is a ginormous problem. And here's the heat of fusion of water in calories. There's several ways to solve the problems, and we're going to use this method. Find the heat needed from the warm water to melt the ice. So we have to do a mass times the heat of fusion. Then we're going to use the heat transfer from above to find the final temperature of the warmer water by using a QSMAT problem. And then we're going to find the weighted average of the two temperatures. There is not a problem like this on your homework, thank goodness. So Q at the phase change is mass times the heat of fusion. And so we get the mass 11 grams times the heat of fusion is 879 calories. So the 11 grams was given in the problem for the ice cube, and we know that that was the heat of fusion that was also given. So 2, find the final temperature of the warm water. Remember, heat lost equals heat gained. So the warm water lost 879 calories to heat the ice cube until it was a liquid at 0 degrees Celsius. So we're going to use QSMAT. So if 879 degrees calories, times 1 calorie per gram degree Celsius, that's the specific heat, times 100 grams, that's the mass. And we have a change in temperature, 20 degrees minus X. So we're plugging and chugging here, and we end up with X equals 11.2 degrees Celsius. That's the final temperature of the liquid water, not the mixture. So we're going to do that next. So step 3, find the final temperature of the mix. We're going to use a weighted average method to find the final temperature of the mix. The final temperature of the ice we know is 0 degrees Celsius. The final temperature of the water is 11.2 degrees Celsius. And we're going to go back to that weighted average we did earlier. 100 grams times that temperature, and 11 grams times its temperature, divided by the total mass, which is 11 times 100, which is 111. And that gives us a final temp of 10 degrees Celsius. So let's do a multi-step phase change problem. I'm just going to keep it on the power slides. When I use the writing unit, it tends not to save when I have to start over. So from worksheet number 1, this is problem number 8. Calculate the amount of energy released in joules to convert 15 grams of steam at 135 degrees Celsius to a solid at 25 degrees Celsius. We can use the following information. So we have the heat of fusion, the vaporization, the specific heat of a gas, the specific heat of a liquid, and a solid. And first we need to cool the steam to the top flat line, the boiling condensing point, which is a QSMAT problem. And then we need to do the phase change, which is we're going to call Q2, and it's going to be the heat of vaporization times the mass. We don't have a change in temperature here because the temperature doesn't change at the phase change. Third, we'll need to cool the liquid from the 100 degrees down to the freezing melting point, which is 0 degrees. And we'll have the specific heat of the liquid times mass times delta T. And then the fourth thing we need to do is the bottom phase change line, which is going to be Q4, it's the heat of fusion, times the mass. And the fifth thing we need to do is cool it from the freezing point down to minus 25 degrees Celsius, which is another SMAT, and you have to use the S of a solid. And then we're going to add all those values up. So here's Q1, pa-ching, there's Q2, and Q3, 4, 5, and then we add them all up. At the end, I put on a negative sign because heat is released. We went down the heating curve, and that means energy was released. It was exothermic. I kept all these values here positive just because it was easier for me to keep track of what I was doing. So section 2, measuring energy. I think that is where we can stop doing our notes. Yes, we can. So those are the end of the notes for worksheet 1, the back side. Kind of like the dark side of the moon, but it's the back side.